Hello everyone, I'm Ying. I'm working together with Jiaxing, Jeff, Minjie, Thomas, and ZZ on this impression store. Okay, and in old days, we believed that an algorithm with ON complexity is already efficient enough. So how about today when N increased very rapidly? So in Bing search log, it increased 60% of data for every 200 days. It's very rapidly. Though we have already enabled parallelism, but the speed of machine is still slower than the increase of data volume. Okay, and also it is an illusion that we can compete over all the data because the data keep changing and it's not clean and not complete, and what we compute is only a sample, right? So we believe that in many applications that the approximate result suffice. Just like Michael had mentioned, want to make trade-off between the accuracy and cost. Now here, let's look at an example in the Bing search service quality analysis. So this is a page view if we want to search the keywords HotCloud. And when user click the first link in the log, we have a timestamp T1. And then when the user switch to the second link, and we have a log of timestamp T2. So let's think about it. If user click the first link and stay there for a long time before switch to the second, or never switch to the second, we say the user must be very satisfied with the first link. And we give them a positive score. On the other hand, with the user after click on the first link and quickly switch to the second, we say user must not satisfy with this result and give it as a negative score. And then when we aggregate all the score, and we can have a view of the service quality, right? So when we group by the market vertical and data plot here. Here is something very interesting that is, one thing is here the outlier. And there are some of the groups with very big, very high score, and some with very small score. Another information is very valuable is that a majority of the groups have this kind of scores. Okay, and in many applications in the real production, we think that is, this kind of outlier or top K detection is very normally used. Different from traditional database, the table is only hundreds of columns. In the search applications, especially data mining pipeline, and the data have thousands of columns. Can we imagine that a query access the data with thousands of columns? So users never care about the raw data. Instead, they want to do the group by and aggregation. And after data group by, and then the data is sparse, that is, there must be some big component and some small component. And we think that is, in many applications, that is the big component analysis is already enough. And then in this work, we propose the impression store that we provide the abstraction of the big data vector. It supports the big component as top K and outlier and mode. And so for storage, it does not need to store the real accurate data. Instead, it just stored impression level data. Okay, and in this way, we can improve the performance of storage, I/O, and make it high scalable. Okay, and let's look at the system design. And the first one is we want the system to be high scalability. That is, any node can process any updates, and also the query, any node can answer the query. Since any node accepts any update, then we need a synchronization mechanism to make the copies on each node to be eventually consistent. And second, we want the system to be storage, memory, and I/O communication efficient. So how to achieve this? We need some good data compression technique, right? And then last, we want system to be high throughput. Once there's an update, we cannot decompress the data and perform updates. So we want the update to be performed on the compressed domain. And also, since we only care about the big component, so we want the decompressed algorithm to find the big component only, without uncover all the data. So how to achieve this? We leverage a technique called compressive sensing. So what is compressive sensing? So given a data vector with length n, It is sparse. Sparse means the sum of component which is 0. And then we random project it into a vector with length m. And how to implement this random projection? This is with just multiple a matrix, a random matrix with size m multiple n. So we say there's a vector with length n and with multiple a matrix with size m and n. As a result, we get a vector with size m. So this is compression, right? And then since here the random matrix phi is not full rank, it's not reversible, so we cannot directly solve the x. So there's a lot of algorithm on computer sensing that aim to recover the x. Okay. Okay, we're talking about the compression. So how about the other compression technique? There are a lot of compression techniques. Why you are using the compressive sensing? And because there are some advantages. And first one is it is decomposable. What does it mean? It means if a vector x can be represented as the sum of two components x1 and x2, and the compression of x can also be represented as the sum of each of the components of x. Is it useful? Yes, let's look at two scenarios. Let's think about it. If the x1 is positioned on node 1 and x2 on node 2, and then if we want to get a distributed aggregation, we can just compress x1 and x2 on two nodes separately. And then we can ship the compressed data to the central node for the aggregation. Then we can save a lot of communication cost. And the other scenario, let's think about, for example, streaming applications. The data keep updating. And then x1, x0 here is the base data. And then the delta x is a change. And then we just compress the change and apply on the compressed domain. Okay. Another advantage of compressed sensing is that there are some heuristic algorithm that is by nature can recover the big component in the early stage, right? And also we improve this compressed sensing algorithm to support recovered outlier and mode. Okay, let's look at the architecture of the system. The first client. Client is responsible for map a table into data vector to translate the SQL into the operations on the vector. And the API here is very simple, support update and the impression level query. And each node in the impression store continuously work on three tasks. First, it aggregates the changes and do the data compression. And second is propagate the change to different nodes according to the synchronization policy. And notice that the communication cost across all the nodes is OM instead of ON. And then each node can just recover the impression level query. Since the recovery algorithm is a matrix operation, so we can use GPU to speed up the processing. Okay, let's look at synchronization. Since the update is randomly issued on each node, okay, and then we need to send the update inside of the network, right? And we have a oracle measurement that is all the nodes should have the same value, right? So we want to make each node value converge to the oracle value quickly. And our synchronization protocol works like this. So for each node, it updates comes from two parts. One is from its neighbors. For example, here is from neighbor P or from neighbor W, and the other updates is from the client. And then the value on each node actually is the aggregation of these two parts. So whenever we found a Y change, we need to send the change to the other nodes. So what value we need to send? We need to send this the Y change after change and minus the data we received from the node, right? So at each timestamp, each pair of send and receive copies may not be the same, but we can prove that this policy can achieve eventually consistency. And actually, this policy can be applied to any loop-free topology. You can use the master-slave topology, and it has low latency but not load balance. You can also use the line topology. It has low latency but good load balancing. And any topology in the between is a good trade-off. Okay? And we're also thinking of many optimizations. For example, we can use GPU for the matrix operation, which can speed up to 30 to 40 times. And also, for each two updates, the change may not be big. Then we can use the information in our last recovery and to speed up the recovery in the next update. Okay, and let's look at some preliminary result. Since our recovery is approximate, then we need some error matrix definition. Here we have two error definition. The first one is error on position or on key, and the second one is on value. Let me use an example to explain. The value on position or key in this example is here. The ground truth is key from 1 to 5, and approximation is 1, 4, and 6. So we see here there's a difference. So the error on the position is 20%. And the error on the value actually is the num2 relative error of the two vectors. And the workload we select is the in the Bing search merge log. After group by the 6th attribute, we get the revenue of S entry totally is 12,000. That is n equals to 12,000 in the vector. Now first, let's look at the effect of m and n on the recovery quality. Let's here, the error bound here means for each of the value m and k, we generate 100 times of random matrix. And then each time, the different random mirror matrix may get different accuracy in the recovery. So we choose the maximum error as the error bound. So you can see here, given the error bound, so M scales linear with K, right? But still, we can see when the error bound is 10% and K is 20, M is only 5% compared with N. And later we see, let's look at the error bound on the value. You see, M is relatively robust with different K. And then let's see the recovery on the big value. Now, when we choose M equals to 800, we can see the top 20 recover is very accurate. When we choose M equals to 300, we can see the top 20 is still more accurate than the rest. Yeah, you can see that is in the recovery, the big component can be recovered with more accuracy. Okay, and then you may ask a question is, you want to only answer the big component. Then in the storage, you can use some other approach to approximate this big component query processing. For example, in the current production, they just use store the top element. If you only want the top K, I can stop top M. The M is equals to your compressive sensing parameter, right? But in this approach, actually, the data after K minus 1 is dropped. So when the data keep increasing, whenever the data value exceeds the K, it can appear in the result. But still, the values in front are lost. So how about compressive sensing? Actually, in the compress phase, we compress all the data. Nothing is lost. One component, as its increase is big enough, it can be naturally recovered. Now here is the result. There's one component who ranked below the top 300. And then we just keep it updated as time going along. And when it is big enough, it can be captured by the compressive sensing. However, if we only store top K, and though it can be found, but the aggregation value is not accurate, right? Okay, and this is our ongoing and future work. you may notice we only support top K outlier and mode, and we want to further explore compressive and to support more queries. And also, so in our system, actually each node maintains a copy of data. So if we enable the parallelism, we can improve the confidence of these samples. Okay, thanks.
Very good talk. Any questions? Anyone? So I'm just curious, is there, in terms of usefulness in terms of the overhead associated with this, is there, have you considered what the implications are, say, with respect to, runtime overhead? How expensive is this to implement?
Until now, I cannot give you a very exact answer because we are still implementing this. But however, we have implemented the compressing over Hadoop for compare with them for a top K query. And we see we can improve 20% of the end-to-end time because we save a lot of shuffling cost from mapper to reducer.
Any questions? Okay, I think we're going to head to lunch now. So let's thank the speaker again.